Hi folks, welcome back. So in a recent video, I shared that Proceda, which is my specialized AI harness for taking standard operating procedures and turning them into runnable AI agents, has achieved state-of-the-art performance on SOP-Bench. So go look at that video if you want to understand what the benchmark is and what the SOTA performance numbers look like. But what I want to cover in this video is an in-depth look at the design of Proceda and how that design is what really enabled it to achieve SOTA performance on SOP-Bench, but with much cheaper models. Proceda itself is open source. It's available on GitHub here. And I also offer a hosted managed version of it running in the cloud at sop.run. All right, so let's look at the design itself. Now, the thesis is that if you have something like an SOP where you have a set of steps you want to execute to achieve some end-to-end business workflow, a harness that is specialized to that use case will beat out a more generic agent, even with a more powerful model. And that's what they did in the baseline. In the baseline, in the SOP-Bench paper, they had two different techniques. One was function calling, and another one was a standard React reason plus act LLM loop, where they gave the entire SOP as one monolithic text document into the system prompt. Proceda has a very different model of how SOP execution proceeds. So let's get into that in a bit more detail. I want to go through all the main design decisions that went into building Proceda. The first and most important one is that the SOP is treated as a state machine. And what I mean by that is that execution proceeds one step at a time. Now, internally, this is modeled as skill step objects, but in pseudocode, you can imagine it proceeding like this, where you prompt the LLM with just the instruction for one step. And then to execute that one step, you might have to do an agentic loop. You might have to make tool calls and reason over the tool calls and do multiple calls to LLMs. But you're still reasoning over that one step. So you have a very bounded scope over which the LLM is reasoning. And only after you finish reasoning through this one step do you proceed to the next step. And this really is crucial to achieving reliable performance, even with cheaper models, because you're really reducing the scope over which the LLM is reasoning. It's not reasoning over the entire SOP, it's reasoning just about one step. All right, decision number 2 is that the way you progress from one step to the next is also structured via control tools. What I mean by that is that I inject two new tools into the tool set used by the LLM. One is complete step and another one is request clarification. Complete step is the tool that the LLM is instructed to call when it has reasoned through and finished this one step. And request clarification is the tool the LLM calls when it needs input or approval from a human. And so these are very structured ways to make progress and get human input and feedback. And because it is structured, you get much higher reliability. The model must call complete step to advance, but also it prevents the model from skipping steps or short-circuiting reasoning through a step. It has to reason through every step in order to make progress. Breaking it into steps also lets you insert circuit breakers like a nudge if the model isn't making progress, or just some kind of hard cap if it's looping through one step but still not able to complete it. This shows up as 100% execution completion rate on the benchmark. So every task went through to completion. There were no execution crashes or infinite loops. All right, decision number 3 is all about context engineering. How do you manage the context as you're going through an SOP a step at a time and making tool calls and doing reasoning at every step? So Proceda has this notion of trimming context if it comes close to the limit. It differentiates between critical messages and non-critical messages. So critical messages are things like, of course, the overall system prompt, which sets up execution through the SOP, the main prompt for executing each step, any input from humans, and non-critical messages are things like the results of tool calls, which often can be pretty large. And all this has a recency bias. So you will trim non-critical messages from older steps while preserving it for the most recent steps. And this really comes in handy when you're executing very long SOPs with many steps, or where every step in an SOP involves many tool calls. All right, decision number 4 has to do with approval gates. And this isn't so much about benchmarking, but matching how humans expect SOP execution to proceed. SOPs will often have steps that require human approval or input, and those can be expressed with these natural language markers. And there's 2 flavors. One is asking for approval after the step completes before advancing to the next one, and another one is asking before the step starts executing. Decision number 5 is also very important for reliability and correctness because it structures the output of running the entire SOP. So rather than the SOP execution ending with some free-form text, you want to actually declare the names and semantics of the output fields you're looking for. And this by now is a pretty common pattern in agent construction, where you try to structure the output so that you don't have to do some kind of fuzzy matching or regular expressions. You just have either XML or JSON, and you can straight away deterministically parse it. Decision number 6 is to have circuit breakers and guardrails, where because you're executing a step at a time, you can have all these limits and thresholds, where if the LLM isn't making progress, you can bail out. And finally, decision number 7 is not related so much to performance, but to observability and auditability. Because you're executing a step at a time, at every step, you can do a ton of logging. What tools were called, what LLM calls were made for this particular step, what approval was requested, what approval was granted. So you can do all this detailed, structured logging at every step. And this is really important in an enterprise context because after the fact, you want to be able to go back and look at these detailed traces for auditability. So I think those are the main design decisions that enabled Proceda to achieve SOTA performance with much cheaper models compared to the baselines in the SOP-Bench paper, which had to use heavier models like Claude 4 Sonnet or Claude Opus and so on. I'll say one more thing, which is that this notion of treating an SOP as a sequence of explicitly demarcated steps and executing it a step at a time not only makes technical sense, but it also matches the mental model of the end user. Because a business user, when they look at an SOP or when they work through an SOP, they don't treat it as one monolith. They naturally treat it as a sequence of steps and make progress through it a step at a time. So this matches the mental model of the user as well. So that was a quick dive into the design of Proceda, which is a state-of-the-art AI harness for SOP execution. I hope you found that helpful. I'll leave links to all this and the GitHub repo for Proceda down in the description. Thank you very much.